Welcome to this IAS distinguished lecture. Um, Today I want to introduce our distinguished guest, Professor Adrian Bejan. He got his BS, MS, and PhD degree all from the same institution at MIT in the early 70s. And he was a fellow in the Miller Institute for Basic Research in Science at UC Berkeley. From 1976 to 1978. He is now the J.A. Jones Professor of Mechanical Engineering at Duke University. Professor Bejan's research covers a wide range of topics in applied physics, thermodynamics, and the constructal law as the law of physics that governs organization and evolution in nature, which is also the major focus of his lecture today. He is the author of 28 books and over 600 peer-reviewed journal articles, and he has a very high H index, which is 55 on the Web of Science. And in 2001, he was ranked among the 100 most cited authors in engineering worldwide. He received the highest international awards for thermal sciences and is a member of the Academy of Europe and an honorary member of the American Society of Mechanical Engineers. He was also awarded 18 honorary doctorates from university in 11 different countries. So it is our great honor to have Professor Bejan with us today. Let's give him a big hand to welcome him.
Thank you, Professor Chow, for the introduction, and I want to thank the Institute for Advanced Study for the great honor of speaking in front of you. I'm both honored and flattered. I thank you for coming to my lecture, speaking primarily of the students. And I came here prepared to accomplish two things. First, to engage you in a review of the principles of thermodynamics, and second, to use my new book as a vehicle for illustrating to all of you, or reminding those of you who know already, why the subject is important. To start, I recognize that that we, all of us, have some difficulty associating words such as life and evolution with physics, because we're indoctrinated to think that life and evolution belong in biology. My lecture today is, in fact, the greatest tribute to physics. To point out that physics, in fact, is the big tent under which everything fits. Or said another way, the laws of physics are respected or obeyed by anything, anywhere in nature. So, and also because we're here in a teaching institution, the approach I'm taking is that of making sure that I define the terms so that you know what I mean when I speak of evolution, life, and physics. I begin with physics. Physics is the, these terms don't come from English. Physics from Greek, nature from Latin, they mean the everything that happens by itself, around us, inside of us. And the human mind from the beginning was inclined to question these happenings and to understand them, so that once understood and summarized, these happenings became principles which empowered the human mind to predict the future, so that humanity marches forward into a future that's safer, better, anyway, better for all of us. So that's nature. Obviously, physics is about everything, the animate and the inanimate. And we are reminded of that truth by images, configurations, I call it organization or the appearance of design, images that are the same while in fact they refer to two totally different realms. Inanimate on the left, the river delta, the animate on the right, the human lung. So the observations of the same kind appearing in the billions, such as these images here, are known as one phenomenon in physics, and one phenomenon in physics calls for its own summarizing statement, which is the law of physics. The table of contents of my presentation has two chapters. The first is, again, to continue defining the terms very briefly, and the second to walk you through examples documented much more clearly in my new book, examples that answer the question of what about us? Why is this phenomenon and principle important to us? I'll walk you through power technology, predicting lifetime, which also means predicting death, S-curve history of things all over, hierarchy, why it is natural, and also what knowledge means in physics. First, evolution. Any of us could, in fact, design and observe this experiment. Water falling on a small area, shown here in green. Over time, meaning rain falling on the area. Over time, a drawing appears. It's obviously tree-shaped. This is the birth of a river basin. The fact is that from one screen to the next, the tape runs to the right. From one screen to the next, the flow gets easier, meaning the architecture evolves. Evolution, as you'll see shortly, means design change. And this evolving happens because the flow system, we call it theonomic system, what you see here in green, has the freedom to change. So freedom, the most obvious thing, the most necessary, and the least talked about feature of a physical system, is now a central concept in my lecture today. And the tape of evolution, running to the right, never stops running. The phenomenon is not the tree or one image, it is the direction in which the movie tape is running. And I saw this phenomenon again by chance. Nobody can predict the hunches. 20 years ago, when I summarized the phenomenon this way, I said for a flow system to persist in time, and that is now the definition of life. To persist in time is to live. It must evolve freely such that it provides greater access to its currents. So the constructal law, the principle I'll be invoking many times today, is nothing more and nothing less than the time arrow of change, which is evolution. Here's another, should be a common example of evolution from the inanimate realm, a plume of smoke. The plumes are as different as the things that are burning. On the left, a curtain of smoke. On the right, a concentrated fire generating smoke. But evolution is such that sooner or later, all plumes look the same, meaning all of them have a round cross-section. The one on the left starts flat, as if coming out of a slit, but at a particular height, which is actually predictable, the plume on the left is the same as the plume on the right. From a longer distance, the brush fire on the right will generate a plume that's very similar to the upper sections of this. Why is this? Because anything that flows has the tendency to configure itself to get through its environment or to give to the environment what it possesses with most easily or greater access. In this case, what flows from the plume to the environment is movement or momentum, literally. Momentum means movement. So now the rest begins this way in a formal sense with a brief review of theonomics. Thermodynamics, as we practice it, we invoke it in fact all the time, consists of two old phenomena and a new one. The old phenomena are energy conservation, or what goes up must come down. That's, or the mechanical equivalent of the calorie. That's known in thermodynamics as the first law. The second classical phenomenon is irreversibility, or a one-way flow from high to low. That's kept in as the second law of thermodynamics. The principle of today is the constructal law, which accounts for this natural tendency of flow architecture to morph freely into progressively better flowing, if you want, configurations. The constructal law, as I said earlier, is about the time arrow of evolution. Here's a drawing I made to show you in one glance the history of thermodynamics. It's a 200-year-old history that began with the gradual merger of two highly successful chapters in science, mechanics and the caloric theory. Caloric theory gave birth to a lost child called the heat trans, which was brought into thermodynamics not long ago. In any case, caloric and mechanics became thermodynamics 150 years ago. And these past 2 decades, another phenomenon, the phenomenon of evolution, and of course the discipline of design came into thermodynamics formally, even though the book of any book of thermodynamics is in fact thick, because it is full of ideas and lessons of how to make a flow architecture better. The thermodynamics book, if it were to be only about the principles, would have maybe 2 pages, the first law and the second law. The book is full of design evolution lessons or stories, and it is the thickness of that is now made smaller and smaller because the principle is known. So now begins my list of examples. I'm not going through demonstrating the validity of these examples. I'm simply walking you through the story of this new book. I showed you the evolution of the river basin. That's water flowing on an area over time in the better and better architectures. This screen is about different kind of water flowing on the same landscape. Animals are basically self-propelled wheelbarrows full of water, swimming, running, or flying. This is the example of flying. The movement is horizontal at a cruising altitude. The movement is happening because the flyer is powered naturally or by a machine, powered to push its environment out of the way, meaning a movement without environmental impact is nonsense. So flight is what you see, and from answering the question of how to make flight easier, which means to happen with a smaller and smaller effort, the conclusion to that is that the speed of flight must be a particular value, which happens to be proportional to the mass of the body to power 1/6, which is also the same as saying that the speed is a particular multiple of the length scale of the body to power 1/2. It is only after this prediction that one gathers the courage to plot together the characteristic speeds of highly dissimilar things, insects, birds, and airplanes. Very shortly, I'll call the airplanes the flying human and machine species, evolving as we speak. And to discover that all these flyers that occurred naturally are in fact representing, or they represent manifestations of the natural tendency summarized as the constructal law. There's another thing to observe here. The cloud of data, in fact, increases from left to right in history. The first were small and many. The most recent are few and large. In other words, flyers, these entities that sweep the landscape possess natural hierarchy. Few large and many small. Just like the channels in any river basin. Few large and many small. What flows is not a river basin, or here the flying carpet. What flows is, what flows is not the one channel or one flyer. What flows is the whole, the river basin, and in this case, the entire population of in this case, a biological flying mass powered by, obviously, fuel of one kind or another. The story of predicting animal movement from the constructal law is a very, very exciting field, about 10 years old. The conclusions from this emerging literature are that they are predictive conclusions. The larger animals should travel faster, according to the proportionality between speed and size. They should wave their bodies less frequently, according to a particular formula, meaning they should appear more sluggish, even though they are faster. Think of the whale or the elephant. They are definitely faster than the carp and the mouse. Should be stronger, should move more mass to greater distances, and you'll see shortly should live longer and travel farther during lifetime. And if you don't believe these conclusions from the constructal law or from your knowledge of zoology data, then you can believe them by looking at what athletes have been doing as they climb up on the winners' podiums. Here are the winners of the 100-meter dash in history. Records are meant to be broken. Speeds increase as the time marches to the right along this correlation. And the discovery, which is from the constructal law, not a discovery, but a prediction, is that to the right, in time, the sizes of these winners should also increase in exactly the same manner as the speed versus body size correlation of all running animals. It's the same for the fastest swimmers. This is the 100-meter freestyle during the 100-year-long history of recorded competitive sports. The average of these data is the same as that for all swimmers. So take it the way you want. Either athletes are evolving like animals. They're certainly illustrating a kind of evolution in a small laboratory, or animals are athletes, okay? But you can witness evolution in our lifetime by reading the sports pages. This is a screen that represents an accurate simulation of a runner, modeled the simplest way possible as a stick that falls forward repeatedly. So the runner has two dimensions, height and size, which is the mass of the runner at the top of the stick. So using, of course, the laws of mechanics, you can predict what happens over time as the stick falls and then rights itself up and falls again. There are two sticks, a tall one, A and B, and a short one, C and D. In each simulation from left to right, the time is the same. So now you can see which stick travels farther during the fixed time. And you can include the two things, because obviously A and B is a longer travel than C and D, that speed comes from size. The taller is faster. And among the tall cases, making many steps so that the falling stick is essentially vertical is also a technique for speed. So now those of you who follow sports, you can understand why certain athletes tall take relatively few steps. That would be like Usain Bolt. And others, also tall, like Michael Johnson, take many steps in order to win races. So with athletics, we achieve several things. We illustrate evolution in our lifetime, which is a great contribution to biology. Second, we predict the evolution of the sport itself, or we educate trainers how to bring up better and better athletes. That was for running tall. In swimming is the same idea. The idea is to rise higher above the water. Here on the right-hand side, you see a swimmer, a very good swimmer, swimming with fingers spread just a little bit, so that the paddle, quote unquote, is the human hand wearing a water glove. So even without a web, meaning between the fingers there are boundary layers of water, the human hand is bigger than it looks, and that means that the swimmer raises his torso higher above the water than otherwise. And in other words, for the animal with the web feet to have developed the web, in the beginning the animal must have learned this technique of spreading its fingers. The other thing we illustrate with this particular discovery is that swimmers, like flyers, move on the landscape in this manner by rising above, even though they do not touch the ground. Here's the airplane touching the ground indirectly by shooting into the ground puffs of air. And again, this predictive power is available if you learn the principle, not only for individual sports but also for team sports. These are data from baseball. In baseball, there are many positions ranging from second base to pitcher, and the average heights of these players during the history of, meaning the current average heights in the major leagues in the United States, are such that the highest speeds correspond to the positions in which the throwing speed is absolutely critical. So speed goes with height. Not only that, but the average height of pitchers in the U.S. during the past century has been increasing monotonically. I mean steadily, not monotonically. There are some bumps there having to do with the 2 world wars. There's another, I mean, the list of predictions is yet to be constructed. Here is one of my most recent pleasures, which is to predict the fraction or the fraction of the body size that is occupied by the legs. You can show that as the body size increases, more of the drawing is occupied by the legs. These would be drawings of the same height. And if you go from left to right, you see that more and more the animal is all legs. This is predictable. It's quite different than the somewhat obvious notion that the bigger the leg, like the bigger the trunk of the tree, the more stout it should look. That is not the phenomenon that I'm predicting here. The phenomenon is the proportions, that the proportion of legs versus total body size. And continuing in this direction of now, in fact, getting closer to the question of what about us, I focus now on the flying species, all of us, the human and machine. This is a summary of a compendium of the evolution of commercial aircraft during its 100-year-long history. So on the abscissa is time, on the ordinate is the maximum, meaning the loaded weight of every new model. What's interesting here is that at any point in time, for example today, if you look on the right-hand side, new models come in all sizes. But the biggest at the very top are, of course, few. The smaller and smaller at the bottom are more and more numerous. That is at a fixed period in time. And sweeping the chart from left to right, the largest models are joined by even larger models. This is quite similar to the evolution of this other cloud here. Time from left to right, many small here, few large over there, and of course time continues to march, so you can, with the chart, this chart you can predict evolution, with this other chart you can predict the evolution of technology. You can predict a lot more. For example, the fact that, again, proportions, the fact that the motors of any new model should be roughly 1/10 of the total size of the vehicle. It's an amazing proportionality shown in the upper right-hand side, and this is just one of several. You also predict that the fuel load should be roughly 1/3 of the body size, that the range on one fuel load covered by the aircraft should be proportional to the body size. And even most interesting, that over time, the wingspan should be essentially the same as the fuselage length, which means that small or large, over time, all airplanes end up looking the same. Just like the birds. Birds are birds because they essentially have this image when seen from above. Let's see what next. Next, another phenomenon, you speak of it quite often, especially in economics and management, economies of scale. It is the fact that the bigger are more efficient. You want something shipped cheaply, you put it on a big truck along with many similar packages. These two charts are from the evolution of machines, in other words, steam engines, from the beginning of history to today. The chart on the left is really well known. Things are becoming more efficient. In fact, this chart should have been drawn as a mountain. The mountain is here, and the dots that you see pinpoint the crest of the mountain, meaning the best of the machines. On the right-hand side is the chart that most people overlook. It is that with increasing power, or it is actually that efficiency itself goes monotonically with the size of the power plant. Bigger power plants are more efficient. Physically, this is predictable because bigger power plants have bigger pipes, meaning orifices through which fluids flow with less irreversibility. They have bigger heat exchangers, which means heat currents that flow with less irreversibility. So losses become smaller in the direction from left to right. This idea is, in fact, the key to predicting another phenomenon, which is that organs on anything that moves as a vehicle or animal should have characteristic sizes. The so-called losses, which are in theonomics called irreversibility or entropy generation, or the destruction of useful energy, plotted on the ordinate, are due to two effects. One is what I mentioned already, that any component which has a particular size, the size could be anything on the abscissa, any component, for example, a pump, or a piece of pipe, or the surface of a heat exchanger, destroys useful energy for two reasons. The first is this descending curve. It has to do with the friction or the resistance to heat transfer. In any case, a resistance that decreases as the size of the component increases. So if you only look at this curve, you learn that big means attractive. But at the same time, the vehicle or the animal must carry this particular component. So that is the reason for the second line, which is a rising line. And that one indicates that bigger is actually not attractive. So the sum of the two lines is the one shown at the top. It is a bucket-shaped curve indicating that the trade-off is also pronounced as the existence of a characteristic size which is characteristic to the vehicle that uses and carries the organ. So to summarize, the fact that big hearts belong on big animals and big jet engines belong on big airplanes is in fact the way nature, this constructal law principle, tends to change its configuration as it moves things on the world map. There's another effect here, which is that over time, when it comes to technology evolving, the pump becomes better. The pipe, if it had a flat cross-section, becomes a pipe with round cross-section. The heat exchanger becomes better, so this descending line becomes even lower. So that means that the characteristic size over time has the tendency to become smaller. This is how one anticipates, without knowing anything about technology evolution, the natural trend toward miniaturization. Things are getting smaller because in that direction, the user of the thing is more efficient itself. This is a one-chart summary of the evolution of the cooling of electronics. The electronics package, for example, your laptop, or originally the phone booth, is a box that generates heat. The removal of heat in this particular drawing is by natural convection. There's a optimal spacing or striation to insert in this drawing. But one feature of the design, which was not discussed until this story of evolution, is that when the length scale of the package decreases, the performance of the package improves. On the ordinate is plotted the packaging, or the heat transfer density of the design. So good versus time is to march to the left. What one discovers is that if the heat transfer mechanism is changed from natural convection to forced convection, say blown air through the package, then this trend toward smaller and better continues, but it continues faster. That means that technology itself, in addition to offering smaller things, offers them with a dramatically different technology, which is forced convection cooling. There's a second transition, which is from forced convection to cooling the same package, smaller and smaller, with high conductivity inserts, and that too is predictable as an abrupt change. So with technology evolution, just like with the evolution of athletics, we have the advantage that we can actually witness evolution and anticipate the future of that particular flow system. In this case, vehicles or anyway, pockets of humanity that are using these devices. In other words, your iPhone is getting smaller and lighter because it is good for you, the user, the carrier. Another trend that's also predicted from the constructal law is the appearance of a vascular or modular design, or in biology is called modularity. You see in the upper drawing the way that every tissue is built. Every tissue is a volume, a flow system, bathed by one stream coming in, for example, arterial blood, and then the stream is distributed over the entire volume. And then the stream is reconstituted into a single stream of venous blood that leaves the volume. The way to bathe this finite volume is, an infinite number of drawings could be made, but the simplest, which is here, the yellow rectangle, it shows you fresh fluid in, bathing the volume, and then the red fluid leaving. The direction of design evolution toward greater and greater flow systems is not by magnifying the first design I show you. It turns out that making a modular design or a construct, a large construct consisting of the smaller designs is much better for the purpose of bathing the volume with greater access, which means in this case smaller overall flow resistance. This conclusion, or prediction if you want, is valid in both two-dimensional and three-dimensional flow. It is also an answer to the very, very, very difficult question in design, which is how do you scale up a small design that works? Meaning like the yellow rectangle, how do you scale it up? You don't scale it up by magnifying it. You scale it up by throwing that drawing away and predicting the right drawing that should belong for the size that you contemplate. Every size has a particular drawing. Now I dig more deeply into what's important to us. First of all, theonomics is really, according to the first law and second law, about converting heat into work or heating into power. Those two laws proclaim that heat can be converted only partially into work. This other fraction is rejected with the ambient. The doctrine is about changing the design inside the blue world, shown here, so that more of the heat is delivered to a user as work. So the two laws account for the transformation, but as I said earlier, the book accounts for what's going on in the blue, and the two laws do not account. In fact, the two laws are about black boxes. The two laws apply to any system, anywhere. The evolution that you see in the blue is the phenomenon captured by the constructal law. And even more, because of the constructal law, we ask the question, what happens to the produced power? Here are the blue designs. Here's the fraction of Q that became work. What happens to the produced power is that the power is destroyed immediately in the process of moving something against the environment. So let's summarize. Heat in, a fraction of it becomes work. The work is destroyed immediately and it becomes heat. So that now you squint, you move away from the screen. Heat in is heat out to the ambient. But because of the design, because of the architecture of the flow system, in the meantime, something moved horizontally against its environment. That is the full picture of power generation and use on Earth, man-made or not man-made. You see there, air currents, ocean currents, animals and vehicles all do this. In fact, if you erase this little drawing and in the dashed rectangle you put Earth itself, you have a heating from the sun, the same heat current then escapes into the cold universe. But on Earth, you have all this movement which does both power generation and then power dissipation, hand in glove. Again, the story continues more examples by using, you take the icon, either the river delta, which is shown here, or the vehicle, or the animal. You can show that the lifetime of the movement is, meaning this time, should be a particular time proportional to the size of the mover to power 1/4, and the life travel should be proportional to the size to a power close to 1/2. That is the way things should be, and that is, of course, what data show across the board from the inanimate to the animate and the man-made. Very recently, while teaching this discovery to my students, I was able to use two even more common examples of movers that exhibit evolution and lifetime and life travel. A rolling stone with initial kinetic energy travels to a particular distance over a particular lifetime, which is predictable. The same with an eddy of turbulence. It moves downstream until it disappears to a life travel at a particular lifetime. The conclusion is the same for both. And the life and is the same proportionality between lifetime and size and the life travel in size, so that the lifetime divided by the square root of travel is a constant for all these things. And also for all of them, the number of rolls from birth to death is constant. Just like the well-known idea in zoology that all animals, small or large, have the same number of heartbeats lifetime or the same number of breaths. You see, so the principle marches you through these discoveries, but the discoveries together illustrate the universality of the phenomenon captured by the principle. Now, this is now the last third of my talk. I take you through a few more examples about us. We move on this landscape in many, many ways. I categorize them as a movement in time and then movement in space. In time, just like the spreading population of, in this case, Brewers East, we move with a particular history so that the territory that we cover in life increases as an S-shaped curve. Slow in the beginning, fast in the middle, slow near the end. S-curve. These are people using radios, people using TVs, people reading one of my papers, actually. So the point is, these people on the landscape, they represent a territory over which something new is spreading. All right? Why is this happening? Well, coming from a principle, it's easy to show why. What is spreading is actually invading the territory through an existing architecture, a dry riverbed or a truck that carries these new iPhones to a string of Apple stores. So the invasion is very much like a military invasion along a well-designed path. Left and right of it are the first who come in contact with the new, and they constitute the finger-shaped area that grows over time. You can show grows in an accelerated fashion. When the invading needle crosses the territory, the spreading continues, but it spreads laterally through diffusion. And that second phase of the phenomenon, I call it consolidation, which really means the filling of the empty pockets. And that is also, that territory is also increasing monotonically in time, but at a decreasing rate. So if you splice these two arcs together, you have the S-curve in your pocket. You have predicted it in a very, very simple manner. So the S-curve is about spreading something on a previously virgin territory. Now, it's not only the spreading, but also the collecting. The new, in this case oil, comes from the area to the point. And what's interesting here is, of course, the answer to how does the constructal law come in. The constructal law is about the evolution of this particular design over time. It evolves in, the constructal law says the design should evolve so that the flowing, either collecting or spreading, should become more easier, which means faster. the evolution should be in the direction indicated by those drawings toward the dendritic kind of galleries, if you want. It is for this reason that mining everywhere on Earth emerges as not single shaft, but dendritic shaft, just like all the other things that you see spreading from point to area. So the S-curve phenomenon is a constructal law phenomenon that's predictable. With it, of course, you can advise all of economics and business on how to distribute things better, how to increase sales, how to increase advertising, and on and on and on. Now, of course, spreading increases over time in S-curve fashion. You have to keep in mind that that doesn't mean that spreading will go on forever, because the S-curve, after all, means that the spreading will hit the wall quietly. The spreading will continue, but slower and slower and slower. Here are three curves that should make you think when you hear that the sky is falling. The first is the S-curve of power production in the US and Great Britain over the past century. That's an S-curve, okay? This is the second curve are the miles driven by vehicles in the US, vehicles being a big group of users of this power, also an S-curve. That means that power generation and power use are not getting out of control. And here's the world population up to 2050, according to the UN. It is an S-curve, also explaining why there has been a so-called population explosion, quote unquote, is because of the technology of power generation, which is at most, let's say, 200 years old. So the future has nothing to do with exponential growth or explosive growth. There's no exponential on the screen. All of us have taken mathematics. We know what an exponential is. It is a function that is always above zero, and it starts being above zero at time equals minus infinity. Okay? That is not the case of anything that has happened on Earth. Okay? There's a start of something at time t equals zero, which is the invention of you name what, or the time when I pour water on the ground. It is after that that the spreading starts. Okay? And the second kind of movement is this one. We flow with architecture that evolves in space. This is the flow between an area and one point. This is the Atlanta airport. Everybody on this rectangle arrives at any point, which means on the area, and let's say tries to get out the terminal, out of the terminal, which is in fact over here. So it's about the area to point flow of people. And you could show that the best shape for this rectangle, which benefits everybody, in other words, which minimizes the travel time in an average sense for everybody, is actually this shape, the one shown on the screen. And that special shape is such that the time to walk is the same as the time to ride, or the time to go long and fast, which is the one in black, is the same as the time to go short and slow, which is the blue. This is the formula. This is the secret behind the natural emergence of any city block. The city block begins at a smaller scale with the black, which is the alley. The blue is the lawn in front of your house. You walk in order to get to the car. Or at a larger scale, the blue are the small alleys, and the black is the first real street, and so on. Streets and avenues, okay? That's the origin of, or the blueprint behind the so-called city phenomenon. Well, keep that in mind, because the city strikes you with a different kind of drawing. It's the grid, either a highly regular one, like in Manhattan, or something that's skewed, irregular, like in an old city. That is an illusion. It's not the grid that flows, It is what flows through the grid. For example, a population shown here in yellow, a crowd getting away from a stadium. That flow is tree-shaped. Or, for example, in purple, people converging on a square for a political demonstration. That is an instantaneous tree-shaped flow. One is, if one is delta, the other one is river basin, okay? And you can actually play, you can illustrate this phenomenon yourself by pouring batter on a waffle iron. I took these pictures myself, and behind me there was a line of people trying to use the waffle iron. But the effort was worth it for this purpose. The Atlanta airport design, this template appears everywhere, and the name for it is hierarchy is a natural tendency. We see it in the design of, the evolving design of freight on the landscape. Few large and many small. All those vehicles are carrying the same stuff, or what most people in biology call the food chain. Few large predators, many small prey, grazing on the grass. The same design is that of the river and the hill slopes. Hill slopes, river between them, slow and then fast. Inhaling and exhaling, this is the design of the respiratory system. The slaughterhouse floor, animal carcass entering as one, and then many parts at both sides being taken out. In the reverse direction is the auto assembly line. Many parts from the side make one vehicle traveling out of the area from left to right. So the phenomenon is the how hierarchy happens. What flows through the area is not a principle. Oops. Oh, okay, sorry. This is now at the largest scale. Air routes over Europe. The long and fast are shown in red. Transversal to them is the short and slow in yellow. In other words, you fly from an airport to another. Well, once out of the airport, you have to find the car and travel to your house or hotel. The template is on the right. Now I begin to summarize this lesson of theonomics with evolving architecture. At the bottom, I start at the bottom. Nothing moves unless it is driven. The so-called useful energy, the thing that is consumed, goes by other names such as fuel or food or solar heating and some other things. Anyway, useful energy is transformed into work. Work is used for the purpose of moving horizontally a mass to a distance. So, using this in order to create movement. Well, the observation, again from air transportation, is that the movement is hierarchical. This is a NASA, image of everybody flying. The busiest, the concentration of flyers is in the aorta of the heart, which is between Europe and North America. Everybody's flying, but sooner or later, like the red blood cell in some peripheral tissue, sooner or later the red blood cell has to flow through the heart. So the movement is hierarchical. It is natural because no single entity or individual designed what this picture shows, and that means that the consumption of fuel is naturally hierarchical. So any notion that those who are busier using fuel will actually cut back, so that those who are not that busy burning fuel will burn more, is against nature. It will not happen. Now, going even farther in the direction of, generalizing or recognizing the importance of these discoveries, we recognize that for us, meaning what's important to us is not only transportation, meaning using fuel in order to move us, but also heating, cooling, fresh water. We need fuel for all these things. All these things added together account for the so-called energy use, which means amount of fuel burned in 1 year, energy use, versus this other measure on the left, which is actually the wealth of the group plotted as a point on this graph. So now we're discovering that the physics, which allowed us to recognize hierarchy in energy use or also movement, is known in economics by another name, which is wealth. So wealth, or economics itself, belongs in physics. This is the bisector, meaning that the y is another name for the x. Okay? If you are tempted to question this drawing because it's about totals, and obviously the US is much bigger than, for example, Cameroon, then the same drawing on a per capita basis shows essentially the same distribution on the bisector, except that the cloud is a bit thicker. It is thick enough to make you question why, for example, on this vertical, meaning at constant fuel use per capita, the inhabitant of Russia is 10 times poorer than that of the inhabitant of the US or Japan. Or if you want, anyway, so the thickness of the cloud is an important aspect, and has to do with the fact that at the top of the cloud are the same citizens who move through the big channels, in other words, the big movers, showing again that movement means wealth, and lack of movement means poverty. Now, movement is happening in these places that are shown in red and orange because of obviously better technology, better science, all of that. It means knowledge. Knowledge means not only the so-called information, but also the putting of that to use. Knowledge means design change that is actually implemented. That is how a machine becomes better. So the better machine in this little sketch is available in the dark. In the dark, there is greater movement, or if you want, faster spreading. The natural tendency of the physical movement is to spread more and more easily, and that means the spreader is actually invading those who do not possess knowledge yet. So that is why it is natural that knowledge is so-called contagious, or that evolution is unstoppable. With this particular slide, you can predict the future of many territories on Earth where this discrepancy between advancement and lack of advancement is striking today. And finally, a little lesson of thermodynamics, to illustrate what evolution means one more time, meaning change in flow configuration in time. Imagine that one of these rectangles is the so-called flow system. It is a system operating in steady state. Wind blows through it steadily, and everything in the system does not change over time, except if there is a, let's call it intelligent entity that changes the internal configuration, a Maxwell's demon, that changes the configuration of the flow system internally. And in other words, from ancient Egypt to Renaissance and then 1800, the drawing changes, and this particular object in the system moves from left to right faster, which means more efficiently, farther. Boat with sails or automobile, the same example. For you to connect today's lesson to theonomics itself, theonomics is about everything you see on the slide, except that before the constructal law, there was no principle proclaiming that drawings should be changing from left to right in this direction over time. That is my lecture. On the left, one more time, the table of contents. On the right, the book that's actually a short book that should be accessible to all of you, especially young students. Thank you very much.
So the fractal description of the constructal law, would that apply in any way to, let's say, the evolution of the universe itself?
Okay, the second part of your question, the answer is yes. The first part, what do you mean, the fractal description of the constructal law? I did not use the word fractal.
You didn't? No.
No, because nothing that I showed is fractal.
No, I was just referring to the tree-like branches.
Tree-like does not mean fractal.
I apologize.
No, you don't have to apologize. This is look, a fractal geometry is a great idea. But a great idea 40 years later becomes, a discussion in which the terms are not defined. A fractal object, according to Mandelbrot, is meaning a drawing that is obtained by repeating an algorithm ad infinitum, an infinite number of times. Nothing like that has been observed. The river basin has, obviously, rivulets. Channels smaller than those do not exist. The human lung has tubules leading to, or starting from, alveoli. Air sacs smaller than the alveoles do not exist. It turns out that the river basin and the lung are predictable, meaning I can make the drawing by invoking the constructor law. So missing all along in so-called fractal geometry of nature has been the law of physics that allows you, with which you can actually predict an algorithm that you would repeat a finite number of times. The law tells you when to stop, at what small scale, so that your drawing looks like the drawing of nature. So missing all along in fractal geometry has been the physics. No physics, okay? Fractal geometry is a technique for making drawings. You pick an algorithm the way that the painter picks a paintbrush, okay? And the fractal geometry shows you a beautiful drawing. It doesn't show you the many more drawings that came out when you pick the wrong algorithm. Same with the painter. The painter has lots of drawings that he threw away. Maybe they become expensive later, long after the painter is dead. But again, fractal geometry is descriptive. Description is the opposite of prediction. With the law of physics, you predict. With these mathematical tools, because that's what a paintbrush is, with that you describe. So that's where the confusion slipped in, and it's worth explaining.
I ask a question from airspace point of view. You use the example of aircraft and so on, also the evolution of human transport means. I think the unit you use is distance, but from our business we will think about speed. Where is the speed coming in your laws and so on? We always try to, as human being, okay, we want to, in the beginning we work, then we take transport, we ride on a horse, then go in a train, whatever, boats, aircraft. And then for aircraft, you use a particular type of aircraft, but we always want to fly faster, higher, and longer distance. Your law seems to describe the distance. Have I missed anything?
Yes, the speed goes hand in hand with is there. The speed is a particular multiple of the size raised to power 1/6. It should be this way in order for the movement to be efficient. What matters to humans is first and foremost not speed. It is the effort that it takes in order to create the movement. We come from fire, in meaning humans with fire as opposed after humans without fire. Why? Because fire empowered the humans to move more easily, to do more things with. For example, to hunt more easily. Then domesticated animals, same direction, making it easier to move on Earth, which means to live. Domesticated animals. I mentioned slaves. Slavery was a construct of human organization that happened in this direction of, in other words, everybody on this earth desires power, physics, not political, power as in physics. So in that desire, now coming back to the aircraft, is what in aircraft technology is decreasing the fuel amount spent per seat on the airplane and 100 meters flown. That is the figure of merit, okay? It turns out that in that direction of evolution of the design, other things happen. The airplane becomes, as you keep seeing, bigger and faster, okay? And at the same time, the aircraft, like the Concorde, that had a very poor fuel spent per seat per 100 kilometers, is destined to disappear, to be non-competitive. Now
that's something sad, isn't it? Because of the most beautiful thing. So beautiful things disappears in life.
Well, I agree, but today's actually news 3 weeks ago is about doing the Concorde better. Okay, in other words, doing it for a purpose where speed trumps, pardon the expression, trumps fuel economy. Okay. But for all of us who are doing the flying, you know, millions and millions every year on top of the existing millions, for the common flyers, what matters is how much you pay for the ticket. Incidentally, those of you who are educated in aerospace, there's a famous chart from the late 40s called the Gabrieli and von Karman chart, what price speed. It is an empirical gathering of performance data, meaning fuel consumption versus speed of the aircraft available after World War II. With the constructal law, most recently in the AIAA journal, we were able to predict the alignment of that cloud of data. We predict, they described 60 years ago. So all of that now comes together as one very, very simple example, one among many. Examples of the same principle, the same tendency.
Thank you for your presentation. I see that throughout your presentation you always uses sizes. So especially even in evolution, I could see that things are getting bigger, things are getting smaller, and I don't really see how fundamental size is important in analysis for life, evolution, and physics, because at the end of the day, size does not really tell me a lot about the physics. If the conclusion that things are getting smaller and smaller, at the end of the day, we are made from the smallest thing in the earth. And the second thing is how even sea turtle, it's smaller comparing to other fish in the sea, but they do live longer than others. And this size analysis get me confused a little bit, maybe.
You've said many things which account for the general observation that nature is complicated, there's diversity everywhere, and there are deviations from the pattern. Such is nature. But in order to discuss, so I'm starting from the end of your point. But the very notion that certain things deviate, like the turtle and the hare, the turtle wins the race because it is intelligent. I don't know. The point is, deviation means that there is a pattern. Deviation from what? So there are things that, like the tree log, falling over and stopping the water from flowing down this channel. Who could predict that that would happen? But the broad picture, meaning the tendency of the flow system, is to flow with the evolving configuration. Size in physics does not mean big or small. It is hierarchy, the coexistence, the tendencies for things to move together, large and small, in a persisting way, as if plotting together to move this way, not the one at the expense of the other, but together in order for the whole to move more easily. You look at the air traffic system or the river and the hill slope. So things are not getting bigger or getting smaller. It is they come in all sizes. The bigger a few, the smaller many. That you saw that with the airplanes. You see it with everything else that in my examples. Here's another point. I also showed you economies of scale. The bigger are more efficient. Well, yes, there is a tendency toward greater efficiency, but it doesn't mean that the territory ends up being covered by big things. The territory will continue to be swept by few large and many small, even though the few large individually are more efficient than meaning better carriers than the small individuals. See that? The bigger and more efficient are not putting the many and small out of business. The bigger depend on the small in the same way as the small depend on the bigger, because together in that combination, which is hierarchical, sweep the area the easiest.
The weight and the mass of something is more fundamental to measure from?
The weight in anything that moves on a landscape, in water, on land, or in the air, that weight is proportional to the horizontal force of which is the resistance that the ambient poses. So, because of gravity, weight actually means horizontal force. Weight is vertical, but because of movement against an ambient, the horizontal force of resistance is proportional to the weight. It's counterintuitive, but if it were not for gravity, a lot of what we're discussing here today would not be an issue. I'm talking about nature as experienced by those who invented this language, meaning 2,000 years ago.
It's an interesting presentation, but since you pick a very provocative title, so I suppose you don't mind to defend it, okay?
Pick the title. I'll tell you the story of the title. But
okay. So I think you present a lot of maybe a collection of data showing the correlations between different factors. Okay, maybe between size and speed, or size and maybe time and that sort of thing. I think that's interesting, but is that really physics or life? That's what my question is. Because correlation doesn't mean physics. Physics meaning there's some underlying principle which is well understood and based on very, very simple logic or principle. And just having the correlation, and the correlation between different set of data is very different. So is that really physics? Okay,
yeah.
That's the first question. The second related question is that really life? Growth is not necessarily life, because life involves a lot of things. Evolution, involve about there is a, for example, like maybe
Okay.
reproduction, or maybe a self repairing, and so on and so on. So is that just the title is just make it interesting, or whether you
No,
have some deep thought on it? Okay, that's what I'm curious about.
No, that's why I began with defining the terms. I began with defining the terms. That is, I defined these terms in physics, not in biology. I defined, first of all, physics and nature. I explained what a phenomenon is, what a law is. I defined in physics. I then defined what evolution is in physics, which means everything. I also define what life is in physics. This is the definition of life in physics. Everything that you bring up is an example of life according to this definition. If it moves, and if it has the freedom to morph while moving, it is alive. How do I know? Because I've been teaching theonomics for 40 years, and in theonomics, the concept of dead state is as old as theonomics. Dead means nothing moves. Okay, so death has been defined in physics. The antonym of death is life. That is the definition of life in physics. Now, if you want to read about life in biology, go ahead. But that is not what I'm teaching with this particular book, but also with everything else that I do and publish. And secondly, no, I did not show you correlations. I showed you predictions. For example, this curve came first. The audacity to plot next to it what zoologists have known for a long time, and also what my colleagues in aerospace have known for a long time, came after. I discovered not only the curve, but the fact that nature, including the human and machine species, obeys the law. I've done this every time. Here, with the athletes, I predicted this. In fact, a student of mine came after teaching animal locomotion, according to the constructal law, and said, "What about runners who win the race?" I told him, they're animals. In the good sense, go and collect the data and plot the speeds not over time, but over size. And there came this graph. Anyway, my work is about prediction, which means theory, which is the opposite of description, which means empiricism. Science is both. But in theory, you predict, and then you check against nature. In empiricism, you observe, and then you try to explain that observation by using existing principles. The point of this entire lecture is that without a constructal law, one cannot predict this or this curve, or for that matter, any of the other drawings I showed you, especially these things in the blue world. Without a constructal law, you cannot predict these. Okay. Your colleague asked earlier about universe. Okay, our most recent time in the news this 2 weeks ago was showing why, meaning because of this constructal law tendency, celestial bodies should have hierarchical sizes, meaning not one size everywhere, but few large and many small. Okay, so the fact that all bodies in space are getting bigger and bigger through accretion, meaning smaller bodies falling on the bigger ones, is not to be questioned. But why is it that these collectors of matter are not growing as big bodies of the same size? Why is it that few large and many small is the population of celestial bodies because of the constructal law.
So that's why galaxies get bigger and bigger as more and more clumped together.
If you know about that, go ahead and connect but if you give me your email address, I'll send you this most recent article. I decided not to include it in this talk, but maybe I should have.
Okay, I have a quick question, which is about the origin of your exponent of the scaling law. So you use this law to predict a lot of the things, which is beautiful, but what's the origin of that scale, the exponent?
Which particular exponent?
Like the velocity of the bird and its mass, and also the length of the runner.
Okay.
Yeah, all of them followed by scaling law, but what's the origin of the scale, the exponent?
Yeah, I'll answer specifically. I told you I was not deriving any of these results in this talk, but if this particular question has to do with the exponent shown here, 1/6. It comes from a very brief analysis of calculating in an order of magnitude sense, meaning scale analysis, the size of the work done on the vertical W1 to lift the weight from where it fell, and then W2 is the work done in order to advance the weight horizontally by a particular step horizontally. The step is not fixed. It could vary, obviously, because the speed of this flying object is not known. So the sum of W1 plus W2 turns out to be a formula of two terms. One term, W1, decreases as V increases. W2, as you can imagine, increases fast as V, the speed, increases. So the resistance of the ambient becomes bigger. Anyway, this trade-off between the two terms gives you you can call it constructal speed, capital V, which happens to be a particular multiple of mass to the power 1/6. Okay? That's the origin of that. And nothing, so again, it's not a correlation, it is a prediction.
But should it follow by any natural selection?
Natural selection, you said? Natural selection, like the question you heard earlier, is language from biology. Why should nature select anything? I ask you, because you use the word selection. From physics, the answer is I don't know. This is the phenomenon. There are other such words, self-optimization, self-organization, self-lubrication, all sorts of things like this have been observed and described. In physics, that is the phenomenon. In physics, when the phenomenon strikes you the same way innumerable times, the physicist or the observer says, I'm tired of remembering all these observations. Here's a statement that summarizes these observations. This is why the constructal law is a first principle. It is a statement that cannot be derived from existing first principles. The first law is a first principle. The second law is a first principle. Colleagues in physics could tell you how thin the book of first principles really is. And the first principle of evolution everywhere is this one.
Just a follow-up question is, does this small and many, is it small and many and big and few, right? Does it apply to only sizes or also importance or anything else? Does it has to do with just physical animals or whatever it is? Does it has to be a size? For example, if I'm as a student observing too many publications and research are published, does it mean many and small? Or does it mean, how should I look at it?
Well, you should look at it the way I look at it. Is that everything is about the movement on the landscape. Movement. look at the S curve. Now you talk about citations, okay? The S curve. It's about movement. Movement of you who benefits from carrying this thing, be that radio or the paper that I wrote. Because if you have it, meaning you have the radio, you survive World War II better. Okay? If you have my paper, you do I don't know what. You may even win the 100-meter dash tomorrow ahead of others. You possess more knowledge. You see, you live better, you live longer. Your descendants inherit more from you because movement is wealth, you saw. That is how you should take it, okay? It is good to possess knowledge. I said it's contagious, you see. That's why, by the way, speaking of, that's why knowledge spreads in all possible forms, including spying and theft, because it is useful.
Thanks, Professor, for your interesting theory. I wonder, according to your theory, is there any endpoint for the evolution?
No. And the evidence is massive in support of saying no. Evolution, if it had an endpoint, would have arrived at endpoint a long time ago.
Well, I think according to your theory, at someday in the future, I think a life can adapt to the situation best. I think there is someday. So why not will that be an endpoint?
Oh, you can look at, for example, the human and machine species answers that particular question very clearly. Sure, the naked body has evolved over a long, long time period to have a lung with just 23 levels of bifurcation. Except that the same naked body also had a brain that evolved to this level where every morning this brain comes up with a better idea of what to do during the day. Brush teeth, or get dressed, or not get drunk, or do I don't know what else, go to school, you see. So what you are no longer a naked animal. You are an evolving, highly complex flow system with tentacles all around the globe. You. And I'm the same. I'm not the same octopus, but we're all as big as the globe, okay? And this sort of vasculature, you represent a vasculature on the globe, meaning flow is coming to you. The things that you buy, they come from, not just Japan, they come from South Africa. That's how big you are. And these things are constantly morphing. And when somebody throws a new gadget in the flow architecture, something a lot newer than the iPhone, then you will flow even better. And that's why you, this global architecture, continue to evolve in this direction. The direction is only one. This forward is what's predicted.
Okay, because of the limitation of time, I think we're going to stop here. Let's give the can to Professor Bejan one more time.